Almost 30 years ago, Andrew Wiles shook the mathematical world by announcing a proof of Fermat's last theorem. The ideas behind the proof transformed algebraic number theory. In this program, we will explore how far we have come since then and how much further we have to go. But first, we have to start from the beginning. What is number theory? One of the central problems in number theory is understanding rational solutions to polynomial equations. One of the first systematic studies of these equations was undertaken in the Arithmetica, a 3rd century text by the Greek scholar Diophantus. For this reason, we now call such equations Diophantine equations. Perhaps the most famous Diophantine equation in history is the equation x squared equals 2. This equation has no solutions in rational numbers. Equivalently, the square root of 2 is irrational. Rumor has it that when the Greek mathematician Hippasus discovered this fact 25 centuries ago, his fellow Pythagoreans were so appalled they drowned him in the lake. The reputation of number theory as a tough subject hasn't changed much since then. Let's consider a second example. An arithmetic progression is a sequence of integers whose differences are the same. For example, 1, 25, 49, 73, and so on. Here the common difference is 24. Notice that the first 3 integers here are all perfect squares. But the 4th one is not. So, are there any arithmetic progressions of length 4 consisting of 4 distinct perfect squares? If we call the squares a squared, b squared, c squared, and d squared, then they would satisfy the equation b squared minus a squared equals c squared minus b squared equals d squared minus c squared. This is a Diophantine equation. We call a solution to this equation trivial when all 4 squares are the same, and so the differences are all 0. This leads to the following natural question. Are there any non-trivial solutions? Almost 400 years ago, Pierre de Fermat proved that there were not. His proof, using infinite descent, was the starting point for modern number theory. So how does one study Diophantine equations? It turns out that one of the key ideas is to take the Diophantine equation and count the number of solutions modulo p for all prime numbers p. One of the main goals of this program is to explain the reason why. Let's return to the equation x squared equals 2. Let's count the number of solutions to this equation modulo the prime p is equal to 3. 0 squared is equal to 0 mod 3, 1 squared is equal to 1 mod 3, and 2 squared is also equal to 1 mod 3. So there are no solutions. If p equals 7, on the other hand, then there are 2 solutions. Plus or minus 3 squared is equal to 9 is congruent to 2 mod 7. You can start tabulating the primes and the number of solutions bp to this equation modulo p for each prime p, and you get an infinite list of numbers bp. But how does this help? There are 2 fundamental reasons, both still conjectural, why point counting is a good thing to do. Understanding these 2 reasons goes a long way to understanding the last 50 years in number theory. The first reason comes from combining 2 key conjectural insights, due in part to Grothendieck and to Tate. These conjectures state the following. If you start with a Diophantine equation x and consider the point counts BP for all primes P, then you can recover the original Diophantine equation from the numbers BP. In other words, there's no information lost by simply studying the set of numbers BP. To be more precise, from the point counts BP, you can recover something called the motive associated to the Diophantine equation. In many situations, the Diophantine equation can be recovered from the motive. But this equivalence on its own, while interesting, is really not enough to justify studying point counts. The key observation, the basis for much of the Langlands program, is the following. For any Diophantine equation, there is another, completely different way to generate the same list of numbers, BP. The reciprocity conjecture says that given any Diophantine equation, there is a shadowy object, an automorphic form, which generates the point counts in a completely different way. The definition of an automorphic form is very complicated. I'm honestly not sure I understand it myself, but at least I can give some explicit examples. Consider the group Z mod 8Z star of integers prime to 8. This is an abelian group of order 4 with elements 1, 3, 5, and 7. There's a homomorphism from this group to the complex numbers, which sends 1 and 7 to 1 and sends 3 and 5 to -1. Chi is a particularly easy example of an automorphic form. Let's consider the function AP, which takes a prime P and outputs chi P. And let's consider the function BP to be 1 plus AP. For example, 3 goes to chi of 3 plus 1 is equal to 0. And 7 goes to chi of 7 plus 1 is equal to 2. For any prime P, it is a theorem that the numbers BP computed using this formula is exactly the same as the numbers BP on this list. This theorem is a special case of the reciprocity conjecture. In this case, it's actually a special case of the law of quadratic reciprocity proved by Gauss in 1798. Gauss's law of quadratic reciprocity is really the first non-trivial example of the Langlands program. It's also the reason why the word reciprocity is used for the general conjecture, even though Diophantine equations and automorphic forms don't look anything alike, except in a few exceptional cases. Here is a second example. Take the following infinite product and expand it as a formal power series in Q. This is another example of an automorphic form. In fact, it's a modular form. Now consider the function BP, which takes a prime P bigger than 3 and outputs the following number. BP is P minus 1 times 1 plus P minus AP plus 1. For example, B of 5 is 4 times 1 plus 5 minus 2 plus 1 is equal to 33. And B7, by a similar computation, is equal to 49. These numbers turn out to be exactly the same as the number of solutions modulo P to Fermat's 4 squares equation. B squared minus A squared is C squared minus B squared is equal to D squared minus C squared, modulo P. For example, if P is equal to 5, the only solutions to this equation are the solutions in which all the a, b, and c, d are all 0, or they're all plus or minus 1, or they're all plus or minus 2. And this makes exactly 33 solutions. This is another case in which the reciprocity conjecture is a theorem. Except in this case, it's not a theorem due to Gauss, but a special case of the Taniyama-Shimura conjecture. Although this particular example goes back to Shimura himself in the 60s. So what if we knew the full reciprocity conjecture? Could we answer all problems in number theory? It turns out that the reciprocity conjecture is only the beginning. One analogy is that reciprocity is like the periodic table. It's an important structural insight, but it's only a starting point. In chemistry, there are many questions you can't even ask until you have the periodic table. Over the last 50 years, we have built a tower of conjectures which don't even make sense unless you assume reciprocity is true. So what consequences can we draw from reciprocity? Here's an example. We've seen that if you start with a Diophantine equation x, you get a set of point counts BP for all the prime numbers p. Using some simple rules, you can define from this a sequence of numbers AP for each prime number p, and then this you can extend to a sequence of numbers AN for each positive integer n. You can package these AN all together into a new function called an L function by taking the following infinite sum of AN on n to the s from n is 1 to infinity. If the real part of s is big enough, this converges and you get a well-defined function in the right half of the complex plane. If, on the other hand, you start with an automorphic form pi, you can also generate a sequence of numbers AN, and you can also write down an L function by the same formula. Except if you start with an automorphic form, you can prove that this L function has an analytic continuation, or possibly a meromorphic continuation, to the entire complex plane. So one consequence of reciprocity is the following. Given a Diophantine equation x, the L function has a meromorphic continuation to the entire complex plane because the L function of x is equal to the L function of pi, where pi is associated to x by reciprocity. Moreover, from the L function, you can also recover the numbers AP. And so the L function should also know everything about the original Diophantine equation. In this way, arithmetic problems about Diophantine equations can potentially be converted into analytic problems about the L function. It's this connection between arithmetic problems on the one hand and analytic functions on the other, which is at the heart of the Langlands program. Let's take the simplest possible Diophantine equation, which is x is equal to 0. Now this equation has exactly one solution modulo p for every prime p. So in this case, AP is equal to 1 for all primes p, and AN is also equal to 1 for all n. So the L function of this Diophantine equation is simply the sum of 1 on n to the s for all positive integers n. This is precisely the Riemann zeta function. So the reciprocity conjecture, proved in this case, implies that the zeta function has a meromorphic continuation to the whole complex plane. In fact, it has a pole at s equals 1. And now the idea is that the zeta function knows all about the equation x equals 0. So what does that mean? What arithmetic information can we extract from the zeta function? If you know anything about the zeta function, it's that its zeros control the distribution of prime numbers. The Riemann hypothesis makes a very strong prediction about where those zeros are. The Riemann hypothesis can be generalized to the L function of any Diophantine equation. But note that this generalized Riemann hypothesis doesn't even make sense until after one has proven reciprocity. But there are more basic relations between the zeta function and arithmetic than simply counting prime numbers. Here are two more examples. The fact that zeta of 0 is equal to -1/2 turns out to be equivalent to the fact that the integers have a unique factorization. This is a special case of the Dirichlet class number formula, which relates special values of certain L functions associated to number fields to the orders of class groups. Here's something more exotic. We know that zeta of -1 is equal to -1/12. How does this statement translate into arithmetic? It turns out that this is equivalent to the following fact. Let SLNZ be the group of integer matrices with determinant 1. Then for n big enough, the Schur multiplier of this group has order 2. That is, there is a universal extension of this group, which is a central extension of degree 2, and all such central extensions are quotients of this group. So this is now a special case of the Birch-Tate conjecture and the relationships between algebraic K-groups on the one hand and the arithmetic of SLNZ on the other, and values of the Riemann zeta function. In particular, the order of the group K2 of Z is equal to 24 times zeta of -1 is equal to 2. Remember, you can't even begin to make sense of such a statement until after you know that reciprocity holds and that the L function is defined, and so you can make sense of these values. We now understand that these class number type formulas have conjectural generalizations to all Diophantine equations and all L functions. Take the 4 squares in arithmetic progression equation. Remember that reciprocity is known in this case. This equation inside projective space defines an elliptic curve. The generalization of the class number formula in this case is the Birch and Swinnerton-Dyer conjecture. If we call this x, the Birch-Swinnerton-Dyer conjecture says that x has infinitely many rational points if and only if the L value of this L function at 1 is equal to 0. But you can rigorously compute, in this case, that the L value at 1 is equal to 0.539, which is manifestly not 0. Now, by theorems of Colley-Vagan and Gross-Zeghia, we know enough about the Birch-Swinnerton-Dyer conjecture to deduce, in this case, that x has no non-trivial solutions. So, how do you prove reciprocity? If you have a Diophantine equation x, we see that we get a set of point counts BP. On the other hand, if you have an automorphic form, you can also get a set of numbers BP. So on the one hand, you have Diophantine equations. On the other, you have automorphic forms. Now on both sides, there are a set of natural invariants which should match up on both sides. For example, for a Diophantine equation, you can take the primes of bad reduction. For example, if you take the equation x squared equals 2, this behaves badly at the prime p equals 2. This reflects the fact that p equals 2 is the only prime for which the two solutions, plus or minus root 2, somehow become the same modulo 2, but not modulo any other prime. If you fix the finitely many invariants on both sides, then you can prove on the automorphic side there will only be finitely many automorphic forms. So conjecturally, you expect on the Diophantine equation side, there should only be finitely many Diophantine equations and finitely many corresponding point counts. So to prove reciprocity, all you have to do is the following. First, show that given an automorphic form pi, there's a way of going from this to a Diophantine equation x, or possibly a set of point counts. Second, show that this map is a bijection. Let's say exactly the same thing in a much more fancy way. After you fix these invariants, Barry Mazur showed that you could capture the point counts by a ring which he called R. On the other hand, for automorphic forms, you can also understand them after you fix these invariants by another ring which you usually call T. Thus, we're now reduced to 3 simple steps. 1, understand the ring R. 2, understand the ring T. For example, why given a pi, you get a sequence of point counts? Or in other words, why is there a map from R to T? And finally, 3, once you have these, understand why R is equal to T. The nice thing is that these 3 steps can often be considered quite separately. What Wiles and Taylor-Wiles did was come up with a general strategy to prove step 3, assuming you know enough about steps 1 and steps 2. This strategy is now called the Taylor-Wiles method. In the 90s, we did know enough about step 1 and step 2 in the special case of semi-stable elliptic curves in order to prove reciprocity for all such curves over Q, and hence for Wiles to deduce Fermat's last theorem. There have been a number of improvements and important tweaks to the Taylor-Wiles method. The early work of Diamond and Fujiwara, and later work by Kissen and Garrity and several others. But the basic idea has stood the test of time remarkably well, and the Taylor-Wiles method remains the key tool for proving reciprocity to this day. That means that progress over the last 30 years has come from better understanding point counts on the one hand, and better understanding automorphic forms on the other. Progress on these 2 problems is what we turn our attention to now. Number theorists study point counts in a more sophisticated way than just considering a set of point counts BP. Given a set of equations x and a fixed prime L, you can consider the étale cohomology groups given by the étale cohomology of x over q bar with coefficients in QL for some prime L. These are finite dimensional vector spaces, but they also have an action of the Galois group of Q. Which acts on V. Now for every prime number p, the Galois group has a special element called the Frobenius element, Frobenius p. This element acts linearly on the finite dimensional vector space V, and if you take the trace of the linear map, you get back a number which is exactly the number AP coming from the point counts. To be more precise, the Frobenius elements are really only defined up to conjugacy, but the trace of a matrix only depends on the conjugacy class, so the numbers AP are well defined. The key to understanding point counts turns out to be understanding these Galois representations. And to understand Galois representations, you really have to understand the structure of these étale cohomology groups. So what is cohomology? One way to think about cohomology is in terms of differential forms. Again, it's useful to consider an example. Consider the equation x times y equals 1. Underlying this Diophantine equation, there is a geometric object given by the complex solutions to this equation. If you know x, you know y, so you can just think about solutions to this equation as the set of all complex numbers x which are not equal to 0. Or in other words, the complex numbers with 0 removed. And we can draw this by the complex plane with the point 0 removed. An example of a differential on x is dz divided by z. Now if I take some loop, I can integrate the differential on that loop. And if the loop is contractible, then Cauchy's theorem says that the integral of this differential form over this loop is equal to 0. On the other hand, suppose instead I take a loop gamma which goes clockwise around 0. Now if you integrate omega over this loop, you don't get 0. Instead, you get 2 pi I. In this case, the homology of c minus 0 is generated by the path, and the cohomology of c minus 0 is generated by this differential form. And there's a pairing between them, which takes a generator of one and the generator of the other and spits out 2 pi I. But this description of cohomology is given in terms of differentials and differential forms. Étale cohomology is defined in a very different way and is given in terms of finite covers. The one philosophy about cohomology you should know is that it should give the same answer however you define it and however you compute it. One of the great early successes of the Grothendieck school was the very definition of étale cohomology. Étale cohomology provided an algebraic definition of a cohomology group, which also knew about point counts. Showing that these étale cohomology groups had nice properties was the key to Deligne's proof of the Weil conjectures. But there is a second way to give an algebraic definition of cohomology in terms of differentials, called algebraic de Rham cohomology. The general philosophy now says that one should be able to reconstruct étale cohomology together with all the point counts from algebraic de Rham cohomology. Grothendieck understood that one should be able to do this, but he had no idea how to do it. And so he posed the question of how one can go from one cohomology group and produce the other. He called this process the mysterious functor. After clues in the early work of Tate, the key to this puzzle was discovered by Jean-Marc Fontaine, who more or less invented the subject now called integral p-adic Hodge theory. One of the key goals of this theory, now realized by the hard work of many people, was answering Grothendieck's question, explaining how to relate the different algebraic versions of cohomology to each other. Understanding what goes on in integral p-adic Hodge theory is a little hard to explain. After all, Grothendieck had no idea how it worked. But one way to give a cartoon characterization is as follows. Take this formula of the integral of dz on z around the loop is equal to 2 pi I. Then you can ask, how can you make sense of this equation modulo p? It turns out that integral p-adic Hodge theory also gives a new and very rich structure to point counts. The biggest step we have made in understanding point counts over the last 30 years has come directly from advances in integral p-adic Hodge theory. Both of these subjects have been closely intertwined. When Christoph Breuil found a new classification of finite flat group schemes, it led directly to the proof by Breuil, Conrad, Diamond, and Taylor of the full reciprocity conjecture for all elliptic curves over Q. In the last 20 years, further insights by Breuil, Mizar, Kolmez, Kissen, Emerton, and many others in p-adic Hodge theory has directly led to a better understanding of point counts and to new theorems in reciprocity. So what about advances in understanding automorphic forms? Remember that the goal is to start with automorphic forms and link them to point counts. The strategy has always been to first relate automorphic forms to algebraic geometry and then use algebraic geometry to get to point counts, or at least get to Galois representations. Now, automorphic forms come in many different flavors. Sometimes the automorphic forms in question have a direct connection to algebraic geometry. But sometimes there is no apparent link to algebraic geometry at all. Let's consider the automorphic forms conjecturally associated not to elliptic curves over the integers, which were considered by Wiles, but elliptic curves over the Gaussian integers, Zi. That is, we allow the coefficients to be Gaussian integers. We've seen two examples of automorphic forms so far. Now we are ready for the third. This is a link consisting of 3 circles called the Borromean rings. Consider the complement of this link in the 3-sphere. Theorems of Riley and Thurston prove that this 3-manifold admits a metric of constant negative curvature and has the structure of a hyperbolic manifold. If you start taking finite covers of this manifold and then look at the cohomology classes of these covers, then the cohomology classes are given exactly by the automorphic forms related to elliptic curves over the Gaussian integers. More precisely, the automorphic forms are certain harmonic solutions to particular partial differential equations. The fact that they are harmonic implies, by de Rham theory, that they can be interpreted as classes in cohomology. But what is the link between these cohomology classes and algebraic geometry? The complement of the Borromean rings is very much an object in the world of Thurston, and a long way from the world of Grothendieck. It turns out that there are 7-dimensional manifolds, which are torus bundles over these hyperbolic 3 manifolds. And those 7-dimensional manifolds are the boundaries of some 8-dimensional manifolds, and those 8-dimensional manifolds can be related directly to algebraic geometry. More precisely, they are the complex points of some 4-dimensional algebraic varieties. Peter Scholze found the correct technique to exploit this connection in order to link these automorphic forms to point counts. But Scholze's results weren't strong enough for the Taylor-Wiles method. But then, a second breakthrough. Cariani and Scholze found a key improvement to Schultz's previous work. The new method gave just enough information about the automorphic forms in question so that, with lots of hard work, one could apply the Taylor-Wiles method. We now know that all elliptic curves over the Gaussian integers satisfy at least a weak version of reciprocity. The full reciprocity conjecture of elliptic curves over the Gaussian integers is now within reach. We can now prove reciprocity for a very wide class of point counts using the Taylor-Wiles method. This has led to many other spectacular successes. New cases of the Artin conjecture, first proved by Buzzard, Dickinson, Shepard-Barron, and Taylor. The proof of Serre's conjecture by Carré and Winton-Berger. The Sato-Tate conjecture by combined work of Clauzel, Harris, Shepard-Barron, and Taylor. The modularity of all symmetric powers of all modular forms by Newton and Thorne. While these results are spectacular, the problem is, from the perspective of an outsider, this wide class of point counts doesn't always intersect with examples coming from Diophantine equations you might actually write down in real life. For example, we now know that all regular, self-dual motives over the rational numbers satisfy a weak form of reciprocity. But what are examples of Diophantine equations which satisfy this condition? If you ask an algebraic geometer on the street to come up with an example, they will most likely only come up with one: elliptic curves over Q. And we have known how to handle elliptic curves over Q for almost 30 years. Fortunately, we have very recently been able to prove new reciprocity results for equations which turn up in real life. Let me tell you about one such result now. Recall that one consequence of reciprocity is that given a Diophantine equation x, the L function of x has a meromorphic continuation to all of the complex plane. This particular prediction actually predates the reciprocity conjecture. It goes by the name of the Hasse-Weil conjecture. Again, so the conjecture is that this is a meromorphic function. On the complex numbers. So, for what Diophantine equations x is the Hasse-Weil conjecture known? Perhaps the simplest example of a Diophantine equation is a Diophantine equation in a single variable, like x equals 0, or x squared equals 2, or more generally, the equation px equals 0 for some polynomial in one variable. Even in this case, we don't know the full reciprocity conjecture. But we do know the Hasse-Weil conjecture. So when the dimension of x is equal to 0, this follows from work of many people, including Hecker, Artin, and Brouwer, and was proved in 1947. What if we go up one dimension? That is, consider polynomial equations fxy equals 0 in two variables with integer coefficients. Now, if you take the complex solutions to such an equation, you get a topological surface which has genus G for some non-negative integer g. For example, if you take the equation y squared equals px, and the degree of px is equal to 2g plus 1, or 2g plus 2, then the genus of x is equal to g. So for what g can we say anything about the Hasse-Weil conjecture? There's essentially one curve of genus 0, given by the projective line. And in this case, you could write the L function explicitly in terms of the Riemann zeta function, namely z to s times z to s minus 1. And so in this case, the Hasse-Weil conjecture follows from facts about the Riemann zeta function. And so the Hasse-Weil conjecture is a theorem of Riemann from 1859. When g is equal to 1, we're exactly considering the case of elliptic curves over Q. Hence, the full Hasse-Weil conjecture in this case follows from the work of Wiles, Taylor-Wiles, and Breuil, Conrad, Diamond, Taylor. That last work from 2001. Now we come to the case of g is equal to 2. For a long time, this was thought to be beyond the reach of available techniques. But there is the very recent work of Boxer, Caligari, G, and Piloni, which proves the full Hasse-Weil conjecture when g is equal to 2, from 2021. We usually think of algebraic curves as falling into a trichotomy of genus 0, genus 1, and genus at least 2, spherical, Euclidean, and hyperbolic. So this last result sounds very promising, but it is a little misleading. For questions of reciprocity, we now understand that instead of a trichotomy, there is really a tetrachotomy, corresponding to the cases of genus 0, genus 1, genus 2, and genus bigger than 2. From our perspective, the case of genus 3 seems hopeless by all current methods. The automorphic forms one has to understand seem completely inaccessible. Unlike the cases we've seen so far, where these forms can be interpreted as cohomology classes, when g is at least 3, they correspond to certain solutions to differential equations which have no known geometric interpretation. In fact, we can't even rigorously compute a single example, let alone relate it to algebraic geometry or prove reciprocity. And yet, in 1993, nobody besides Andrew Wiles had any idea at all how to prove reciprocity for elliptic curves over Q. Mathematics is full of surprises.